Hello everyone, my name is Peng. I'm a senior software engineer working for Microsoft AI platform team. I'm going to share some update around ONNX Runtime training work. As we shared previously, ONNX Runtime has been designed for addressing few problems, including reducing production model latencies, making it possible to deploy Python-trained models with C# or other programming languages. There are also some needs to run the model on different kinds of devices. For example, the mobile devices, as my colleagues Tom and Scott introduced earlier in the ONNX Runtime mobile presentation. All those requirements are from inferencing scenarios, and ONNX Runtime solved them pretty well. Once we extend to the training area, we see increasing demands to train the large model efficiently. The ONNX Runtime has been proven to be a highly performant inference engine with cross-platform support and extensible architect for either custom operators or hardware accelerators. Training feature is introduced in the past months and now is still in a preview stage and showing promising results on some of the internal models. As of our design principles, we would consider ONNX Runtime would be a generic framework for training deep neural networks. Similar with inference support, we would allow developers to extend with custom operators for trainings. The transformer models find most of its applications in the field of NLP, for example, the tasks of machine translation and time series prediction. It has also been applied to image processing, showing a competing result compared with the convolutional neural networks. On the other hand, training transformer-based architects can be very expensive, especially for long sentences. So those kind of models are becoming a good starting point for us to focus. Last but not least, customer demands would be super important for the production direction too. The chart on this slide shows the ORT training architect. As we see, data scientists will still be able to stick to original trainer code built by PyTorch or other frameworks. Those models would be converted to ONNX model representing the model structure. We usually call it a forward graph in the training scenarios. ORT at the backend would take the ONNX graph in, then handle the complexities including building a training graph, do the graph optimizations, and finally run the graph efficiently. And the backend is also a good place to incorporate innovations including MSR deep speed, parallel, and MACTRAINs, those kind of techniques. So far, ORT has the capability to run training using both data parallelism and horizontal model parallelism. The sample of how a PyTorch model runs the training with ORT. The flow is a bit out of date when we are working on a new design recently, while most of the concepts remain to be still valid. Roughly saying, the PyTorch model would be converted to ONNX graph first. Afterwards, ORT build the training graph including mixed precision setting up, auto-diff graph building, graph optimization, finally set up distributed training before scaling out to multi-GPUs or multi-nodes. More specifically, ORT supply a loss function to the forward graph as a first step, build the gradient graph step by step, removing unnecessary computations, compose Adam optimizer. Finally, we got a fully training graph. Let's see some result about ORT training acceleration. Here is some proof numbers. For some cases like the integration with Office services, we could see 1.4x higher throughput using ORT. That means for one single training recipe, ORT could reduce almost half of the time to get the training completed. Beyond the listed BERT, GPT-2, Robota XL models, we also see promising speed up in our development for even larger models, 1.5 billion, 2 billion, 2.5 billion, and even larger sizes. Compared with some open source high performance sport training implementations using same training recipes here, ORT brings over 22 to 25% speed up on the throughput. Another highlight here is ORT could run 2x of byte size than PyTorch on one single GPU. That's the reason you could see half of the accumulation step is needed in ORT training than PyTorch. Beyond one single node, ORT scale will up well to 512 GPUs that we observed in the large A100 clusters. Some of the proof gains come from the CUDA kernel improvements we initially did for the bird large models. And all the optimizations are proven to be reusable and applicable for other transformer-based models, in our cases like Robota, GPT-2, and BAT. Yeah, we also provide good coverage for different graph-based optimizations, essentially kernel fusions, in-place computations, and so on. Memory efficiency also plays an important role on the better performance. With buffer reusing, minimizing the memory fragmentations, ORT could run 2x the byte size than PyTorch for very large, as we mentioned earlier. Similar observations apply for the GPT-2 medium training. We could train it on 16 GB V100, while PyTorch hit out of memory issues. Definitely, this memory saving would benefit the large model trainings as well. The last thing I want to share is how existing models can onboard ORT for the training. Yeah, this is where we call it the front-end integration. The way we provide currently require few lines of code change, including model descriptors, ORT trainer construction, replace training loops. This sometimes bring quite some big overhead for the data scientist, so we have been working on a new approach called ORT module to make the integration easier. As shown in the slides, only one line of change is needed in the new design. So you could always check ORT repo for the latest progress and announcements about the ORT module development. If you have interest to try ORT training out, here are some links. For any feedbacks, contact ORT teams on the GitHub, please. Thanks for your time. Bye.